Hello and welcome to GENBAND Learning. My name is Eric Skripczak, and in this video we are going to cover the distributed SBC10 content. These first few slides are going to introduce some concepts that we're going to analyze in more detail in follow-on slides. The SBC is going to provide security for us. That's going to allow us to be protected from malicious internet attacks, such as denial of service attacks or hacking attacks into your network. Again, we will discuss these points more in depth in the follow-on slides. It's going to hide your network addressing topology. Customers are going to have a public-facing IP address for SIP signaling and a separate address for public RTP audio. And then there will be a SIP signaling address and audio address on the private side. Connectivity, we're going to be able to manipulate the SIP headers and SIP messages coming into the system. We can seamlessly handle IP version 4 to IP version 6 and do NAT Traversal. We're going to be able to go ahead and provide quality of service measurements of your actual phone calls so that you can pull reports and do things like traffic policing. We can have bandwidth limitations to limit rates, provide rate limiting on phone calls, and do call admission control. And we can also go ahead and prioritize emergency phone calls. Okay, the SBC is basically a firewall, like the firewall we see here. You're going to have two IP addresses on the public side and two IP addresses on the private side. One of those IP addresses is going to be for SIP signaling traffic, typically on port 5060, but it doesn't have to be. The purple arrow we see here is the audio IP, public and private sides. A lot of telcos want to front end their SBC with a firewall. You absolutely do not have to do that. The SBC is a firewall. The SBC is only going to allow certain things through if they come in on this IP address and they are on this SIP signaling port, typically 5060. Again, it doesn't have to be. And if the audio comes in on this IP address and port range, everything else will be blocked. This is going to provide connectivity from the customer's IP phones to your SBC and get it into the application server or switch. The SBC is going to set on the boundary. The phones might have an IP address of 192.168.1.2 if it's a residential customer. Most residential modems would be set up in that addressing range. That phone would send a message, request for telephony, into your SBC, into a particular IP address and port range, and the SBC would look at it and say, oh yeah, I know what this is, and it would throw it over to the application server or switch for call handling. The audio, most of the time, when customer A calls customer B, the audio will come up to the SBC. Primarily when you have a bank and a car dealership, and they're trying to call each other, they are on different IP networks. Those IP networks do not trust each other. That would be a hole in corporate security. So we bring the audio up to the SBC and hairpin it through the SBC on the private side so that we can go ahead and connect party A's audio path with party B's audio path. So we've got a secure network there setting on the boundary. Okay. Here we see the SBC provides secure access and session management across two or more dissimilar multimedia networks. That is a very wordy way of phrasing, again, bank, car dealership, two customers, two very different IP networks. The bank cannot call the car dealership on its own. That call has to connect up into the SBC. The switch, the application server, would have to help set up that call. The audio for both legs can be pulled up to the SBC, so while the bank and the car dealership don't trust each other, they can hit the IP address on your public-facing side, and your internal core network can complete that call and connect the audio paths. The SBC also is used to provide Bandwidth management. Bandwidth management can mean a lot of different things. We're going to have IP layer rate limiting. We can limit the number of calls per second, the number of SIP messages, so there are multiple places that we can place call limitations on. We will again see this in more detail in follow-on slides. We can be configured to handle routing. A certain call can go somewhere based on the IP address and VNet VLAN that it came in on. Quality of service, service level agreements. Basically, in a nutshell, and we'll see this again in follow-on slides, the SBC can measure call quality, and it can embed that call quality into the billing record, the call detail record. That can go to some place where we can aggregate reports. And then NAT Traversal, again, the SBC is riding that NAT layer, getting addresses in on the public side and connecting them through to your private network. Okay, we mentioned this briefly just a few minutes ago, but the biggest type of hack you can wind up with VoIP is typically either a sniffing attack or a denial of service attack. A denial of service attack is a fairly easily understood thing. What would happen here often is, I hate your company, or I have malice in my heart for your company, or I've sent your CEO a ransom demand, wire me $2,000 to this bank account or I'm going to shut down your network. For whatever reason, I have a nefarious intent in my heart for your company. What I would try to do is I would come on your network as a known trusted user so that I could sniff the packets. I could see, what is my SIP line port setting? Where are these packets going? Ah! Here's a session border controller address. Great, isn't that lovely? Then what I would do is set up a hacking program to throw in thousands of requests for telephony per second against that IP address. My goal would be to shut down all of the CPU processing power so that none of the real traffic gets through. If you have blacklisting turned on the SBC, what can happen is the SBC will look at, oh, I received an invite, it failed. I received another invite, it failed. I got yet another invite, it failed. And if we see a certain amount of these in a certain period of time, blocked, bye-bye. We're no longer going to pay attention to you. We are going to ignore all traffic from that IP address, just gets dropped, period. And then what would happen is, if enough time had elapsed and I hadn't received any of that type of traffic, I could open that back up. And if I saw it again, I could blacklist it for a longer period of time and open it back up. Eventually, we could put those IP address ranges on a permanent blacklist condition. Another thing the SBC can do for us is detect traffic rates. You might have a number of different things here where a customer has negotiated a telephone call for a 64 kilobit per second phone call, and yet they're trying to run 20 megabits per second through that line. It's probably something they're trying to run a Hollywood movie or some other point-to-point data transmission through your network, but they would be stealing a lot of bandwidth used for telephone calls. We could log that, we could drop the call, we could generate alarms, and then tell you that something like that happened. Now, as far as thresholds go for limiting, again, I've already mentioned we can limit based on the calls per second, the number of SIP invites, the number of IP packets. We can do this at multiple places in the system. Individual endpoints can be configured on the SBC. So I could configure this on the endpoint level. I could configure this under a group of endpoints that have been grouped together. I could configure this on the main SIP signaling address, which we call the realm, or a system level, which would be global for everybody. We'll take a look at this a little bit more a little bit later. Now, with regard to call emission control, I did steal a little bit of my thunder. We can limit on number of calls or the number of sessions that you have established, or the IP packet. So we can limit on any of those three places in the network. Okay, now regarding quality of service level agreements, VoIP is fairly unique as far as VoIP phone calls are typically point to point. User A calling user B. In order to get any kind of quality measurement for that phone call, I need to bring that phone call up into the SBC. The audio for both legs are going through the session border controller, so I can look at packet loss, jitter, latency, other perceptual quality values, and I can embed that information into various fields within the call detail record, and then you have the ability to push that information up to something like the GenView 1 EMS. If you had an older system, you would have been pushing this up to the RSM, and then you can go ahead and pull metrics, pull reports based on this call information embedded into the call detail record. The following examples showcase the type of QoS and service level agreement statistics the SBC might give you information on. Okay, bandwidth call admission control, we would be basically telling you the bit rate coming through for the various signals. I've already mentioned that we could calculate jitter, packet loss, latency, quality factors, which is a measurement of an R factor value. We can also provide things like answer seizure ratio, network efficiency ratio, basically what percentage of your calls were abandoned before they were actually established, post-dial delay. You're going to have these types of reports that you can go ahead and run on the solution. And when you need to pull a report, you could say, okay, this is the source number, this is the destination number, or this is the source number for this period of time, these consecutive days, etc. Now, the SBC can be configured so that it knows what your emergency call numbers are. Let's say you've limited customers to 20 calls per second because you're primarily selling to businesses. And let's just say that the call admission control limit was 20, and somebody made a 21st telephone call that was an emergency call. If you have provisioned your emergency numbers into the session border controller, you can go ahead and the SBC would say, oh, they're limited to 20, but this is a 21st call. But guess what? It's an emergency call. I'm going to allow that to go through as a 21st call. And then we could go ahead and let that go through. When somebody else hung up, that would become our 20th call in the system. And of course, those calls also embed into the call detail records. Now, the big problem you're going to have with a lot of customers is their phones are behind a NAT layer. They're on a private IP address side, and you're getting calls in from the public IP address side. So that phone, again, the earlier example I used, 192.168.1.2 is the phone's IP address, just to make something up. The problem here is we have no idea how to get back to that device. When that device says, I'm telephone number at 192.168.1.2, what does that mean? There could be 20 million devices on the planet right now with that IP address range because that was commonly put into most home router networks as the 1.1 address being the primary. There's no way of reaching that device. So what happens is the SBC, when it gets the SIP invite, it's going to say, oh, here's the SIP invite with the IP addressing range. I received this invite from this public IP address, and it would append that public IP address into the SIP message in a via header. We are presuming that if we get back to that IP address responding to that particular message, that device will connect us through that subscriber. That means you don't have to have complex NAT discovery protocols like STUN and ICE on the customer-facing side. So again, we've already talked about this. We're going to go ahead and detect the NAT layer automatically. We're going to append the SIP invite with the NAT layer so everything just works. This eliminates, again, the need to have application layer gateways turned on inside the home residential subscribers firewall. Now, protocol normalization. My, what a big word that is. Let's talk about protocol normalization for just a second. There's a couple of different types of protocols that we may need to normalize. First of all, let's say you're doing a lot of pure interconnects. There are 4 main protocols in a trunking message configuration for SIP. A business trunk might be an aggregated circuit out to a customer premise. There is basically the Cisco model, the Sonos model, the Nortel model, and there's an RFC compliant instruction. So you have a Cisco trunk device that needs to talk to something on Sonos networks, or a Sonos that needs to talk to a Nortel, or a Nortel that wants to talk to an RFC. Obviously you have more combinations than that, but to not belabor the point, you can provision these devices as static devices on the session border controller, and what's going to happen here is the SBC will say, I received an invite from that IP address, from that port. It's configured as Cisco. I'm going to look for to and from information embedded into the SIP message, embedded in the Cisco format. And then we need to make a routing decision. Where are we going with that? Based on the to and from information, we're going to Sonos or Nortel or some RFC compliant device. I need to rewrite those SIP headers to be Sonos compliant with to and from information the way Sonos wants to see it. This is the first type of protocol normalization. We can also do SIP to Signaling System 7 or ISUB SIP to Signaling System 7, ISUB to SIP. We can go both ways. So we can convert SIP to SS7, SS7 to SIP. So we have a number of different ways of normalizing protocols in the network depending on what it is you're trying to connect. So the SBC has the ability to provide man-in-the-middle interconnect functionality for these things. And stateful call management capabilities, again, we're just saying that we're getting something in on this side that's Cisco, and it might go out Sonos, Nortel, RFC on the other side. Big deal there. So we can also look for poorly implemented devices. If you have SIP devices, sometimes they may become corrupted, perhaps intentionally, perhaps they just unintentionally became corrupted. The point is you're getting malformed SIP messages into your SBC. We can watch for that and we can shut those down so they don't get passed on. And if we had devices that are sending in bad stuff, we could go ahead and turn blacklisting on as an example. And again, just a moment ago, I did mention we have the ability to convert SIP to ISUB and ISUB to SIP. Sometimes you're going to have networks that deal with Signaling System 7 or ISUB, and they're going to be on one side or the other, and you're going to need to be able to convert between the two. So again, I've already kind of alluded to this, that different vendors use different protocols. They're all SIP, but the way they embed to and from information into a SIP message is very, very different between Cisco, Sonos, Nortel, and the RFC. And of course, we've already discussed that we can handle that seamlessly. We can normalize those protocols on the inbound and outbound side. And they're going to be, the normalization is going to be controlled via rules. So you're going to create a rule saying, I want to do this manipulation or that manipulation. You could create rules for things like header manipulation. For example, you have a customer's device that's sending something in SIP that's not correct. It's not the way it needs to be for your network. And you keep talking to that customer and saying, hey, you know, this is not coming in properly, can you fix it? And they keep going, no, we don't know how to do that. The SBC could be told to strip off this Nortel header and insert this Nortel header as an example to make something correct for your network. Another example of manipulation controls that could be governed by rules are Some SIP devices want a SIP 183 ringing, and you can convert that to 180 or a 180 to a 183 as an example. So with the SIP normalization, the header normalization, there's going to be two ways of doing this: enhanced header manipulation and flexible message manipulation. If you just needed to convert a whole bunch of 180s to 183s, 183s, 180s, so when the call comes inbound, maybe the call is passing in an invite with a certain message type, 180, 183, whatever, and it needs to be converted to the opposite on the other side, we would convert it both ways in both directions. So we're going to have an inbound on the private side and an inbound on the public side, outbound public and private, and we're going to be able to go ahead and manipulate those headers based on that. So again, we're going to have rules here that are established. Again, there's two ways of manipulating the SIP traffic: enhanced header manipulation and flexible message manipulation. Enhanced header manipulation is the older way of manipulating telephone traffic. Flexible message manipulation is the newer way of manipulating telephone traffic. You can use both of them together. I might, for example, use enhanced header manipulation to modify SIP codes and change the actual SIP messaging with flexible message manipulation as an example. The primary difference between EHM, enhanced header manipulation, and FMM, well, first of all, EHM is older. FMM came about in the release 9.1 timeframe. EHM allowed you to change certain things in the SIP message, but not everything. FMM, you can extract parameters and save them for the duration of the telephone call. You can change any aspect of the SIP message regardless of what it is. FMM is vastly more powerful than EHM. EHM is the older way of doing it. With FMM, we can insert, modify, delete anything in the SIP message. You can do anything. EHM basically was trying to protect you from yourself. You were not allowed to modify SIP headers used for call processing, for example, to and from. In FMM, you can modify anything. You can write traps. You can send entries to logs when you make a modification. And again, we've already kind of alluded to this. FMM can manipulate any part of the SIP message: SIP requests, status lines, headers, bodies, message bodies, anything in the SIP message can be modified with FMM. Okay, the SBC does provide full media support. Media support just basically means, again, customer A calls customer B. They're both on your private, they're both on their own individual private network, so that audio comes up into the SBC. The SBC would help the devices set up a phone call in conjunction with the application server or switch. Phone A would send its list of codecs, code and decode, the things it can use. G711, G729, G726, just as some examples, maybe some video codecs if the phone has video capability. That list is transmitted to the party B telephone. The party B telephone will look at the list that party A provided and say, I will pick the first codec in party's A list that I can do. Okay, we're going to agree to use this codec, and the call just seamlessly goes through. In SIP, generally it's peer-to-peer. The switch doesn't typically get involved in that. But what happens when a customer has modified their network so their SIP device is using only G729 and this customer is using only G711? That is a bad situation that hopefully doesn't happen. For over a decade, I've been telling telephone companies that they need to have some codecs in common with all of their phones, all of their SBCs, all of their PSTN gateways, all of their media resource functions, media servers, so that problem doesn't happen. But you can have customers that get in and tweak their equipment. And if they can't agree on a phone call, the call dies, unless you have transcoding. If you have transcoding, the SBC is capable of sending that call to its transcoder device, and it can convert in the middle between 729, 726, 711, 729, all the different codecs. And basically we can go ahead and allow them to complete their call even though they're using different codecs. And we see here on the slide at the bottom, G711, A-Law, U-Law, G729. These are a small list of codecs. This may not be comprehensive. Codecs are coming out all the time. If you're watching this video and you don't see a codec on here your customers want to use, don't necessarily panic. It may already be incorporated into the platform. It would be good to consult your salesperson, your sales rep for GENBAND. Now, another big thing that can happen with VoIP is you have customers on legacy phone circuits trying to pass a fax through. The problem is with IP devices, they want to see faxes come in using T38. So the SBC can be set up to detect the fax, and it can convert G711 fax to T38 one way and the T38 to G711 the other way. Again, we're just converting protocols because we are the man in the middle. Another thing we can do is we can support IP version 4 and version 6 interworking. Again, we're just sitting in the middle. We don't care if we're talking to IP version 4 or version 6 networks. A lot of things are going to come in and hit us, and we'll just seamlessly work with all the devices there. Now, earlier I mentioned the SBC was a firewall. That is true. We're going to deny everything except layer 3 IP routing and layer 4 session TCP UDP. We're going to basically only allow certain things in if they're on the right port, on the right IP address. Everything else is just automatically blocked. And again, we're riding the boundary between your public and private network, trying to maintain that edge so that customers have a public-facing address they can get into for a request for telephone call, and then we would shut that over to the private IP addressing side of your network. So when a SIP message is received into your network, we're going to look at each message to make sure the SIP syntax is correct, it's formatted properly, we understand the source and destination addresses, the checksums associated with that SIP message all match. If we don't get all of those things correctly, we have options to drop the message, set an alarm, etc. We're going to go ahead, and when we have established a good phone call path, we're going to open a pinhole to allow people to register to the device, to the application server or switch, and then we're going to recognize that endpoint. A lot of the devices hitting your network will probably not be known to the SBC. The SBC can either be set up and configured in phone call mode or interconnect mode. What I mean by phone call mode is that you have a lot of business or residential or both customers. Those accounts are not built on the SBC. The SBC is hard-coded. I received SIP traffic on this IP address in this range. I'm going to throw it over to this pair of application servers, these switches. And once the switch or the application server validates the registration is valid, I will cache that registration. And then from that point forward, I'll know that IP address device. They're going to be recognized in my database for the period of time it registers. When you're in interconnect mode, the primary difference is the SBC knows those devices. You're going to specify this is a Cisco device on my network, this is a Sonos device on my network. They're going to have fixed IP addresses, known ports they're going to come in and utilize. So for your dynamic traffic, your traffic built on application servers, that would typically not be a subscriber built on the SBC. We would cache the registration for the devices requiring pure interconnect, converting Cisco to Sonos, Sonos to Nortel, etc. Those devices would be built on the SBC. Now we've already talked about it, but we can provide session, rate layer, IP rate layer limiting. We could limit the number of calls, the number of SIP requests, the number of IP packets. Again, we're trying to prevent customers from flooding your network. So you could allocate a certain amount of calls per second, certain amount of SIP invites per second, a certain number of IP packets into the SBC to prevent denial of service attacks. A customer's equipment could just go bad and start trying to flood your network. Again, we have different mechanisms to deal with that, from blacklisting them, denying them, etc. Now, what's going to happen here is there are rate limits that can be established in multiple places. We could just set everything at the system level and be done, and that would be fine. We could configure individual endpoints so that maybe customer A was allowed 20 calls and customer B was allowed 30 calls. And then those rate limits could inherit up. The endpoint rate limits cannot be larger cumulatively when you add them all together, 20 calls, 30 calls, 40 calls. Your overall system rate limit would need to be higher than 20 plus 30 plus 40. But we can set rate limits in multiple places. Now, I've already said that we did have the ability to limit the number of calls, the number of SIP invites, the number of IP packets, and if they exceeded that, we could drop that information, we could send an alarm, we could respond or not respond. You do have the ability, again, with emergency calls to exceed any of those limits. This concludes this portion of video. Please check for the next video in this learning series.